Welcome in the 7th class of separation axioms, topological spaces. We have covered T0 spaces, T1 spaces, many theorems and examples from T2 spaces, and once again here we are with more theorems on T2 spaces. So first theorem what we are going to take today is, write down the statement of the theorem first. The theorem is, if or you can say in a first countable space, first countable space we normally denote it by 1 0 space. So in a first countable space in which if you can directly write a first countable space in which every convergent sequence has a unique limit is a T2 space. That means Hausdorff space. What we want to prove, first try to understand the statement of the theorem, that there is a first countable space in which every convergent sequence is having a unique limit point. Then what we have to show that then the space is a Hausdorff space, is a T2 space. So we will prove this theorem by the method of contradiction. We will suppose that there is a first countable space in which every convergent sequence is having a unique limit, and then we will suppose that the space is not Hausdorff, and we will arrive at some contradiction which will show that the space must be a Hausdorff space. So I'm starting with, let X top be a 1 0 space. 1 0 space, you understand that it is a first countable space. So let X top be a 1 0 space in which every convergent sequence has a unique limit. We have to show that this space is a Hausdorff space. Suppose if possible, X top be not T2. Suppose this is not a T2 space. If it is not a T2 space, what will be the property then? Then, for any 2 points x and y, distinct points of x, and for open sets, G containing x and H containing y, G intersection H will not be phi. Because if G intersection H is phi, then you have obtained 2 open sets G and H which are disjoint. One is containing x, one is containing y. That means the space is Hausdorff, T2, which is not, because we have supposed that the space is not T2. That means for every 2 distinct points x and y, you are unable to find 2 disjoint open sets. Whenever you will have 2 open sets, one containing x, one containing y, their intersection will not be phi. Okay, now we will move ahead. Now I'll move ahead with the theorem, with the proof. Since the space is given to be first countable, we know that in a first countable space, for every point x, there exists a nested local base at every point. We are having 2 points x and y. At the point x, we must have a nested local base at x. For the point y, we must have a nested local base at y. Nested local base, you understand, that is a monotonically decreasing local base. So since x top is 1 0, first countable, there exists a nested means monotonically decreasing. There exists a nested local base at every point of x. And if there is a nested local base at every point of x, that means there must be a local base at small x, there must be a nested local base at y. So we must have local bases at the point x and y. So this I have written here. So therefore there must be a nested local base at x, say bx, and members of bx, since it is a nested local, in fact it must be countable also, because the space is 1 0, so this should be a nested monotonically decreasing countable local base, you can say. So there must be a nested countable local base. So here it must be a nested countable local base at x. So this must be a countable, and if it is a countable, you can name it the members of this base as simply b1, b2, b3 and so on. And similarly, and there exists a nested countable local base at y, say by, and the members of by are, you can say b1 dash, b2 dash, b3 dash and so on. One thing is clear, that if you take any member from here and if you take any member from here, that means you take any bn and you take any bn dash, or you can say bm dash, their intersection cannot be phi. Why? Because if this intersection is phi, this bn is a neighborhood of the point x, is an open set containing x, and bm dash is an open set containing y. So you are having an open set containing x, an open set containing y, and if their intersection is phi, the space will be housed off. But you have supposed that the space is not housed off, so open set containing x and open set containing y cannot have empty intersection. There must be non-empty intersection. So that means for every b1 and b1 dash, the intersection is not phi. In general, you can say bn intersection bn dash is not phi, so therefore there must exist xn belonging to bn intersection bn dash. And now we will talk about this sequence xn. We will talk about this sequence xn. Look at bn and bn dash, these are the decreasing members. That means b1 contains b2, b2 contains b3, b3 contains b4. The sets are going continuously shrinking, going smaller and smaller. These open sets containing x, they are getting smaller and smaller step by step. And G is also an open set containing x. So there will be a stage when you will approach that stage. After that stage, every member of Bx will be a subset of G. And similarly, there will be a stage after which every member of By will be a subset of H. So you can say there exists N1, N2 belonging to N such that for every N greater than or equal to N1, your Bn will be a subset of G, and for every N greater than or equal to N1 and for every N greater than or equal to N2, your Bn dash will be a subset of H. And if I take maximum of N1 and N2, take M to be maximum of N1 and N2, then for every N greater than or equal to M, your Bn will be a subset of G and your Bn dash will be a subset of H, which means Bn intersection Bn dash will be a subset of G intersection H, and you are having Xn here. You are having Xn in this set. So that means after M, all the Xn will be in G intersection H. So Xn belongs to G intersection H for every N greater than or equal to M, which is a contradiction. Because if Xn belongs to G and Xn belongs to H for every N greater than or equal to M, G is a neighborhood of X, H is a neighborhood of Y. If Xn belongs to a neighborhood of X for every N greater than or equal to M, that means your Xn converges to X. And Xn belongs to H for every N greater than or equal to M, and H is a neighborhood of Y, that means your sequence Xn converges to Y also. That means you are having a sequence Xn which converges to X as well as to Y, which is a contradiction. Why? Because you are given that every convergent sequence converges to a unique point, and here you are getting a contradiction because your sequence Xn converges to two distinct points X and Y, and this contradiction arises because our supposition was wrong. And what we have supposed that the topological space is not T2 space, not Hausdorff space. So we are wrong. The topological space must be Hausdorff, must be a T2 space. So this was the first theorem of this lecture, and now we move on to the second theorem of the day. And second theorem states that if X and Y, if X and Y are T2 spaces, then their Cartesian product X cross Y is also a T2 space. Is also a T2 space. This is our next theorem. So proof is very easy. What is the proof? Let us move towards the proof. We have to show that X cross Y is a T2 space. So what we have to do? We have to take 2 points, 2 distinct points from X cross Y, and we have to find 2 open sets, one containing the 1 point, other containing the second point, and their intersection must be Y. That is enough to prove that X cross Y is a T2 space. So let X1, Y1, X2, Y2 be 2 distinct points of X cross Y. I have taken 2 distinct points of X cross Y, and now I'll try to find an open set G containing this, an open set H containing this, and G intersection H must be Y. That will be enough to show that X cross Y is a T2 space. Now, X1, Y1 belongs to X cross Y. That means your X1 is in X and your X2 is also in X. So your X1 and X2 are in X. But your X is given to be a T2 space. So therefore, there must exist open sets. There must exist open sets G and H such that X1 belongs to G, X2 belongs to H, and G intersection H is phi, because your X is T2. Now your X1 is in G, your Y1 is in Y. X1 is in G, Y1 is in Y. That means your X1, Y1 is in G cross Y. Similarly, your x2 is in H, your y2 is in Y, so your x2, y2 must be a member of H cross Y. Now what about intersection of G cross Y and H cross Y? Use your distributivity. Simply you will get G intersection H cross Y, but your G intersection H is phi, so it is phi cross Y means phi. Another thing, G is an open set in X and Y is a topological space. And you know that if Y rho is a topological space, the set itself is always open. So Y is open. G is open, Y is open, that means G cross Y is open. H is open, Y is open, so H cross Y is open. Now look at what you have proved. You have taken two distinct points x1, y1 and x2, y2 from X cross Y. You have obtained two open sets G cross Y and H cross Y. One containing x1, y1, another containing x2, y2, and their intersection is also phi. And we have proved that X cross Y is a T2 space. Now this theorem can be extended to a class of Hausdorff spaces. So I can write that product of any non-empty class of T2 spaces is a T2 space. Earlier we have taken product of two spaces. Now I am talking of product of any class of T2 spaces. That means I am talking of product of xi where I belongs to lambda. The proof will be again very easy. How to do? You write it as x, say some member x delta, cross product of rest of xi's. That means I belongs to lambda, but I is not equal to delta because delta I have taken separately. What you have to do? As in the previous case, just take an element x1, x2, then x delta and so on. Similarly, y1, y2, y delta and so on. You just concentrate on these two. X delta not equal to y delta are two members of particular that x delta. But since this x delta is T2 space, there must be two open sets. You can say G delta and H delta. G delta containing this element, H delta containing this element, and their intersection is phi. Now the job is almost over. You have taken G delta from here, so take G delta, cross with rest of the spaces, you take these as it is. I belonging to lambda, I is not equal to delta, and H delta cross product xi, I belonging to lambda, I is not equal to delta. This is your G and this is your H. This is an open set. Each of these xi's, x1, x2, x3, leave x delta, all other, they are all open sets because the space itself is always open. So all these are open and product of open sets is open, so G is open. Similarly, H delta is open and each of xi is open, so H delta product with product of xi is also open, H is open. So G is open, H is open. Your G contains this point, your H contains this point, and if you take intersection of these two, that means G intersection H, what you will get? You will get G delta intersection H delta cross product of the rest of the sets I belonging to lambda I is not equal to delta, but since this set is phi, G delta intersection S delta is phi, so this is your phi, and phi intersected with any set is, phi with Cartesian product with any set is phi, so this is phi, that means your G intersection H is phi. What you have done, you have taken two distinct members of the product and you have obtained two open sets G and H, one containing this point, the second containing this point, and their intersection is phi. So that means the product space is also a T2 space, is also a Hausdorff space. So here I am going to stop this video. With more theorems and more proofs, wait for the next videos. We'll cover not only the separation axioms, after that we'll cover nets and filters and many more topics. Thank you. Thank you.